السلام عليكم ورحمة الله. كيف الحال يا شباب؟ إن شاء الله تكونوا بكل خير. طبعا زي ما قلت لكم إنه اليوم عندنا محاضرة تسجيل، فرح نستكمل فيها طبعا اللي هو اللي بدأنا فيه بشابتر 1 بخصوص الفيكتور Algebra. Okay, so this is the recorded lecture. And we're gonna continue talking about the vector algebra we have started in the last lecture. Let's share the screen and view my notes. These are my notes. Okay. Last time we talked about the definitions about the scalars and vectors, and we had some examples of scalars and vectors. We talked also about the vector field and the scalar field. We defined the unit vector and we showed how to find the unit vector of any vector A. Okay, we started with section 1.5, which talks about the vector addition and subtraction. And we reached to this point where we can find the addition of the vector addition of two vectors using two rules. The first rule we mentioned that it's the parallelogram rule. And we said that we assume that we have two vectors. This is vector A, and another vector, let's call it B. Okay. So we want to find a third vector, which is vector C. C is equal to the addition of A and B. Okay, so we start with the parallelogram rule, and with the parallelogram rule, we finish this shape to make it a full parallelogram. So we draw another vector parallel to B like this, and we draw another vector parallel to A. Okay, now the parallelogram is finished. So the summation of A and B, which is vector C, starts at the point between the two vectors to the other point in the parallelogram. Okay, from the heads of the two vectors to the tails of the two vectors. So this is vector C. Okay, and this is the parallelogram rule. This is rule number 1. The other rule, or the second rule, is the head to tail rule. The head to tail rule. Okay, in the head to tail rule, again, we have two vectors. This is vector A, and this is vector B. Okay. Now what we do is in the head to tail rule, we draw vector B at this point. At the end of vector A, we draw vector B, okay? Then the addition, or C, which is the summation of the two vectors, is we start at the head of vector A and we end at the tail of vector B. Okay, this is vector C. C equals A plus B. Okay, this is in the case of vector addition. Let's do the same with vector subtraction, okay? First, we start with the parallelogram rule, like this. We want to find, let's see, D equals A minus C. Sorry, A minus B. Okay, so we start with the parallelogram rule. We have vector A in this direction. Okay, this is A. And we have B in this direction, but this time we don't need vector B. Actually, we need minus B, okay? It's A minus B. So what we do is that we flip the vector B to the other side, 180 degrees flip. So this is minus B. Okay, and then after we have drawn the vector minus B, we finish up the parallelogram shape. So this is parallel to minus B, and we have another vector that is parallel to A. Okay. Okay, so now the rule says that we start at the heads of the two vectors and we finish at the other corner. Okay, so we start here between the two vectors and we finish at the tail or at the other corner. So this is D. This is vector D. Okay, so D equals A minus B. Now we want to do the subtraction now using the head to tail rule. So what we do, we have D equals A minus B. Okay, first we draw the vector A. Okay, and now this is the vector B. Here we have the vector B. Now what we do is we make, in this case, we made the two vectors, we started at the head, tail, head, tail. Now what we do is here, we make it head, tail, tail, head. So we bring up vector B, A, the orange one, and we put it here. Okay, this is A. I haven't changed anything with A. It's the same direction, the same length. So I can put A wherever I want. So now I put A here, and then I start, it's A minus B. So I start at the head of A, and then move to the head of B. This is how we make the subtraction, like this. So this is vector D. And we, okay, so if we look at the head to tail rule, for the case of addition, we draw the two vectors, head, tail, and then we start at the head of the first vector and to the tail of the other vector. But if it's a subtraction, we put the vectors in this way, head, tail, tail, head, okay? And then we start at the head of A and end at the head of B. If it was A, this is because it's A minus B. If it was B minus A, okay, if it was B minus A, what we do is we start at the head of B and then to the head of A. So it should be the other way around. Okay, if it was B minus A, again, what we do, this is A, and this is B. Okay, and B minus A, we start at the head of A. We start at the head of B and finish at the head of A. This is, you know, B minus A. Okay, this is how we do the vector addition and subtraction using the graphing method. Okay, let's get back to the notes. Okay, there are some, as we are talking about vector algebra, then the laws of algebra all apply to the vector addition and subtraction. The three laws of algebra that apply to the vector addition and subtraction. First thing is the commutative law. The commutative law, if we have A plus B, we can flip the order of the vectors so it's equal to B plus A. Okay, so the order of the addition is not important. The other law of algebra is the associative law. So if we have three vectors A, B, and C, and first we start adding B and C, and then we add A to the result, it's the same as if we start adding A and B first, and then we add C to the end result. So it doesn't matter where you start the addition, okay? And the third law of algebra that applies to the vector addition is the distributive law. So if we have a factor K, constant, it's a constant factor, okay? And this factor is multiplied by the summation of A and B, then we can distribute K to be multiplied by A plus KB. So these are the three rules of vector algebra. And in case of multiplication, if again we have a constant factor, which is K, multiplied by a vector, K times A is equal to A times K. Okay, these are like common sense laws that apply to vector algebra. Now let's move to section 1.6, okay, which talks about position and distance vectors. Yeah, position and distance vectors. So we will define two kinds of vectors in this section. First, we start by defining a point in the space. Let's define a point P in the space. So let's draw the Cartesian space. This is the x-axis, this is the y-axis, and this is Z, okay? And this is the origin. Now let's say we have a point P somewhere in the space, okay? This is P. P has the coordinates X, Y, and Z, okay? Because it is located somewhere in the space at with X component X in the X direction and component Y in the Y direction and component Z in the Z direction. Okay, now we can, this is only a point, it's not a vector, okay? But we can associate with this point, we can associate a vector that goes from the origin all the way up to the point P, okay? A vector that goes from the origin to the point P. This vector, we will call it R sub P, okay? And we will call it a position vector for the point P. So R sub P is a position vector of point P. Okay? Each point in the space, in the three-dimensional space, has a vector, a position vector associated with it. Now let's see here, we said the components or the coordinates of the point P are X, Y, and Z. So let's define the, let's see how we find the position vector of this point. The position vector is equal to X, the component X minus the origin. By the way, the origin is a three-dimensional zero. So 0, 0, 0. 0 in the X direction, 0 in the Y direction, and 0 in the Z direction. Okay? Now, yeah, how to find the position vector of point P. Okay? So first, we have the component X of the point P. So X minus the X component of the origin, which is 0. So X minus 0 along what? Along the X direction, plus Y minus 0 along the Y direction, and plus Z minus 0 along the Z direction. Okay, so which is going to be X A sub X plus Y A sub Y plus Z A sub Z. Okay, so this is the position vector of the point P, which is X, Y, and Z. Okay, let's say we have a point in this space, and this point is located, for example, let's say somewhere here, point Q. The coordinates of Q are 3, 1, and 5. So you move 3 units in the X direction, and 1 unit in the Y direction, and 5 units in the Z direction to reach this point. Let's put it here. Okay, 3, 1, 5. 3, 1, 5. So if I ask you to find the position vector of point Q, then what you do, you say R sub Q is the position vector for point Q, which is equal to 3A sub, which is equal to 3A sub X plus A sub Y plus 5A sub Z. Okay, it's as simple as this, how you find the position vector. Okay. طيب. Now let's say we have 2 points in space. Okay. The first point is point P, which has let's say the coordinates are x1, y1, and z1. The components of point P is x1, y1, and z1. Okay, and let's say we have another point in the space, and that point is called Q. Okay. Q, let's say Q is here. This is point Q, okay? And the Q has coordinates which are x2, y2, and z2, okay? Now, each of these 2 points has its own position vector. So P will have its position vector, which is R sub P is equal to x1 A sub x plus y1 A sub y plus z1 A sub z. Okay, and the same thing applies to point Q. So we have another position vector to point Q, which is R sub Q, which is equal to X2 A sub X plus Y2 A sub Y plus Z2 A sub Z. Okay, now let's say we want to find a vector that goes from point P to point X. Okay, a vector that goes from point P to point X, and we want to find this vector. Let's call that vector to be R sub PQ. Okay, so why we started with P? Because the vector starts at point P and finishes at point Q. So that's why we write it like R sub PQ. If it was to start at point Q and end at point P, then we write it R sub QP. Okay. Now, R sub PQ, we call it R sub PQ. We call it a distance vector, okay, that starts at point P and ends at point Q. Okay, now how we find RPQ? Actually, it's very easy. R sub PQ is equal to the position vector of P, which is R sub P, minus the position vector of Q, which is equal to X1 minus X2 along the X direction plus Y1 minus Y2 along the Y direction plus Z1 minus Z2 along the Z direction. Okay, so this is the distance vector between any 2 points. Okay, of course, if it was if the vector was going from Q to P, then we will have the same result, but we will multiply this vector RPQ by a negative sign. So RQP is equal to what? To the negative sign of RPQ. It's the same magnitude, but it's the same magnitude, but it's the reverse direction. Okay. Okay, good. Right. Now we could find the distance vector between points P and Q, RPQ. Now, if I told you, if I want you to find the distance between P and Q, what you do now, if I ask you about the distance between the 2 points, then that means I'm asking you about a scalar quantity. I'm asking you about the magnitude of the distance vector, okay? So the distance, you just take the magnitude of the RPQ or the magnitude of the RQP, okay? Because I'm asking about the magnitude of that vector only. So the distance only, if I ask about the distance only, then that means I'm asking about a scalar quantity, okay? It's not a vector anymore. But if I ask you to find the distance vector from point P to point Q, then that means I'm talking about a vector. So you have to be careful with the direction, okay? So the distance between P and Q is equal, distance is equal to the magnitude of R sub PQ, which is equal to the magnitude of R sub Q P, okay? Which is equal to what? Which is equal to x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared, all we take the square root of the whole thing. Okay, this is how we find the distance. Okay. So we talked about the position vector. And I mentioned that the position vector, Shabab, it's always, you know, it's always a vector that starts at the origin and ends at the point. So this is the position vector, and then we have defined the distance vector or the displacement vector. We can call it both the distance vector or the displacement vector, or sorry, we can call it the distance vector or the displacement, because the word displacement itself means a vector. So if I ask you to find the distance vector, or I ask you to find the displacement between 2 points, then it's a vector quantity. Okay, so the distance vector from P to Q, okay, then we define it, or sorry, okay, this, I think I had made a mistake. Let's see. Okay, sorry, Shabab. Okay, again, I said we have a distance vector going from point P to point Q. Okay, so we write it R sub PQ. So P is the starting point and the Q is the finishing point, okay? So when we want to find this distance vector, what we do is we use the components of the destination point minus the components of the starting point, okay? So here, okay, so I have to change this. So RPQ is equal to R sub Q minus R sub P, okay? Which is equal to X, okay? Which is equal to X2 minus X1 A sub X, Y2 minus Y1 along the Y direction, and then Z2 minus Z1 along the Z direction, okay? And this is true. R sub QP is equal to the negative sign of R sub PQ. And here for the distance, we don't care about the direction, okay? Because it's a scalar quantity. Okay, let's get back to the notes then. Okay, so if we have 2 points, as we mentioned, P and the Q, and we want to find the distance vector from P to Q, so we use the position vector of Q minus the position vector of P. So the distance vector, we call it the distance vector. Sometimes we call it the displacement, and sometimes we call it the separation vector between 2 points. They're all the same. They're all equivalent to each other. Okay. Okay, if a vector B is a vector field, okay, it's a vector defined over a region, okay, so it's a vector field. If this vector field is given by this notation, like constants only, like in this example, 3 along X direction plus 2 along the Y direction plus 10 along the Z direction, then that means that this vector field is uniform. It has the same magnitude in every single place in the region, okay? So like an example of this, if I say, okay, I want to measure the temperature in this room, okay? And I take so many points in this room and I measure the temperature in these, like let's say I have 100 points in this room, 100 different points, and I measure the temperature in these 100 different points, and then I see that the temperature in every single point is the same. It's like 24 Celsius. Okay, then I say that the distribution of the temperature in this room is uniform. So we say that the temperature in this room is a uniform field. Okay, it's a scalar field, but it's uniform. The same applies here. If you have the same magnitude of the vector in every single point in the region, then we say that this field is uniform. Okay, but if the vector, but if the quantities in the vector field region depend on the place of the particular points, then we say this vector field is non-uniform. Because if you want, let's say the vector field B is a velocity of so many particles in a region. Okay, if the velocity in every single particle is the same, then we say it's a uniform vector field. But if we measure the velocity and we get different amounts of velocities in each single place, then we say it's a non-uniform vector field. Like in this example, the amount or the magnitude of this vector field at any single point depends on the location. See, here we have xy, here we have y squared, here we have xz squared. So it depends on the location of the point where we are measuring the field, the quantity. Okay. Let's have one example before we stop today's class. Okay, the example says, if we have two vector fields, okay, one is called A and the other is called B. Vector A is given by 10 a sub x minus 4 a sub y plus 6 a sub z, and B is equal to 2 a sub x plus a sub y, okay? So both of them are uniform vector fields. We are asked to find some calculations from these two vectors. Part A asks us to find the component of A along AY. Okay, let's go to the whiteboard and do the example there. So we have, let's change the color. Okay, example. So we have vector A to be equal to what? 10 minus 4, 6. 10 minus 4, 6. Okay. This is vector A, and then vector B is equal to what? It's equal to 2 and 1. 2 and 1, okay. 2 a sub x plus a sub y, okay? So part A, we're asked to find the component of A along AY. So find the component of vector A along A sub y. What does this mean? It's asking us to find the component of A in the y direction. The vector A has 3 components. One component is in the x direction, the other component is in the y direction, and the third component is in the z direction. So the question asks us about the component of A that is along the y direction, which means what? Which means this is the component along the y direction, which is, it is equal to -4. Okay, we don't say -4 a sub y, no, because the question itself is telling us that the component is already along y. So we just put the amount of that component without giving it a direction. Okay, now let's move to part B. Part B says, find the magnitude of 3a minus b. Find the magnitude of 3a minus b. 3a minus b, okay? So we want to find the magnitude of 3a minus b. To do this, let's define a third vector, call it c. C is equal to 3a minus b, okay? Now we want to find the magnitude of c, okay? Before we find the magnitude of c, what we do, first we evaluate c. So c is equal to 3 times a. A is equal to 10 a sub x minus 4 a sub y plus 6 a sub z. Okay. Minus b, b is equal to 2 a sub x plus a sub y. Okay, let's work this out. So we have 30 a sub x minus 12 a sub y plus 18 a sub z minus 2 a sub x minus a sub y, okay? Now we want to collect the terms together, like each two terms in the same direction, we collect them together. So we have 30 and minus 2. So we have 30 minus 2 along the x direction. And then we have minus 12 minus 1 along the y direction. And then we have 18 plus 0 along the z direction. This is equal to what? 28 along x direction minus 13 a sub y plus 18 a sub z. Now we found the vector c, okay? Now the next step is to find the magnitude of c. The magnitude of c, how do we find the magnitude of c? It's equal to 28 squared plus 13 squared plus 18 squared, and we have the square root, okay? So this should give us a result. We have 28 squared plus 13 squared plus 18 squared equals, and then we take the square root of the answer. Okay, the square root is equal to 35.73. Okay, then, so the magnitude of vector C is equal to 35.73, which is equal to the magnitude of 3a minus b. Okay, now let's see what we still have. And vector along a plus 2b. Okay, part C asks for find a unit vector along a plus 2b. Along a plus 2b. Okay, so we have a summation of two vectors, a plus 2b. We want to find the unit vector along this summation. So let's define a new vector d. D is equal to a plus 2b. Okay, let's find the value of d. So d is equal to 10a sub x minus 4a sub y plus 6a sub z plus 2b, 2 times vector b, which is 2a sub x plus a sub y. Then we have 10 plus 4 along the x direction minus or plus 2 minus 4 along the y direction plus 6az, okay, which is equal to 14a sub x minus 2a sub y plus 6a sub z. Okay, now we found the vector d. What is required is to find a unit vector along d. Okay, so we need to find a sub d. So a unit vector, the magnitude of that unit vector is 1, and the direction of that vector is along d. So we call it a sub d. A sub d should be equal to what? To d divided by the magnitude of d. Okay, d, we have already found d, which is this vector. It's 14a sub x minus 2a sub y plus 6a sub z. Okay, and we divide by the magnitude of d, which is 14 squared plus 4 plus 36. We take the square root of this, and we get the unit vector along d. Okay. It's equal, okay, so 14 squared plus 4 plus 36, sorry, okay. 14 squared plus 4 plus 36. Okay, then the square root okay, so this should be equal to 1 divided by, or it's like this. So we have 1 by 15.36. So the square root of this thing is equal to 15.36. We have 14a sub x minus 2a sub y plus 6a sub z. Okay, then this is the unit vector along d. It's a unit vector along d. So to make sure it satisfies the unit vector conditions, if you evaluate the magnitude of this vector, it should be equal to 1. Okay, evaluate, you try at home, you evaluate the amount of this whole vector, it should give you a magnitude of 1. Okay, and of course it's in the direction of d because we have the same vector d exactly divided by a constant value of 15.36. So the direction is not changed. So direction of the unit vector is the same as the direction of d. Okay, okay. Okay, let's stop at this point, and I'll see you on Monday. Okay, Assalamu alaikum.